Okay, great. And so we'll keep going here, get to the main event. Um, Currently, this is the LAPG's present board. You can see the offices here on the left-hand side, and on the right, the other directors. Um, we are a open organization. The board meets monthly, generally online and in person these days. It's usually the first Monday of the month in the evening, starting at 6 p.m. The next meeting is March 6th. If you are interested in getting involved in the organization further and providing some support, get in touch with us through our email, and we'll be sure to include you. You can log on and see what goes on, or you can show up in person. But we're certainly always perpetually looking for more help to make these things happen. The other thing is that we would like to make our website even more functional than it is. So at the bottom here, you can see we have multiple pages where we announce upcoming events. We've got a job board. We don't have a lot of postings right now, and we'd like to see all the good companies that are within our footprint here provide us job postings, and we'll get them right up there. So if that's something that interests you, please consider doing it. You will see in the coming weeks a whole lot of events being posted, both for the LIPG as well as for the New York State Council of Professional Geologists. But please consider contributing. As far as upcoming events go, we generally have, webinars and quarterly dinner meetings at the third Thursday of the month. In next month, on the 16th of March, we're having an in-person dinner meeting. Regenesis is going to be the speaker. The exact topic will come out in the announcement. I can tell you that we've been trying to locate a venue somewhere in the Nassau-Suffolk County border area to make it a little more convenient for our Nassau members. So keep a watch out for that. 20th of April, we have a webinar. We're just waiting for confirmation from our speaker, but it will be geologically, hydrogeologically oriented, and it should be a good talk. The 18th of May, we've got someone from the USGS in Denver. It'll be an online webinar, geophysical mapping of Yellowstone's hydrothermal plumbing system. That ought to be a great one. All of these we are, applying for or already have received PDH credits, so keep that in mind. And we are always looking for speakers. We would like to really see membership give us a little more help and come on out and say, hey, I'll do a presentation. I've got something cool to talk about. So please keep that in mind and consider it. As far as field trips this year, we're thinking right now, tentatively, we're going to repeat the field trip to the Museum of Natural History in the city to see the Hall of Gems and Minerals. We did it last year, and we had a great turnout. The museum redid the hall. It was awesome. And if you like looking at rocks, God, they have it really well organized. The displays are phenomenal. It's really comfortable. There's a lot of space. So think about that. Watch for the announcement. And then in August, we're hoping to have our summer canoe and kayak trip and picnic that we've had over the last, we didn't have it during COVID, but we had it last year. We had a great turnout, had a wonderful day. We did it on the Nissaquag River and had a picnic afterward at Nissaquag State Park. So that's good stuff. Upcoming events from other organizations. The Long Island Geologists is having the 30th conference that Dr. Gil Hansen, our featured speaker tonight, has organized and kept this going through all these years. It's usually on a Saturday, as you can see here, April 15th. It's going to be online this year. The programs will be put on the website. You can see down at the bottom, the abstracts are still, coming in. So you can see the deadline for that is March 15th. And it's been a good one. I haven't been able to attend all 30, but the ones that I did go to, had a great time, learned some good stuff, and saw some really good speakers. Even the students doing their research have always been really neat. So keep that in mind. A little bit for a plug for the New York State Council of Professional Geologists, which is our sister organization. In March 16th, there'll be a virtual membership meeting. And you can go to their website. You can see their website at the bottom there. Find out more about that if you'd like to attend that. They've got a fundraiser going on in April called Geology Rocks. They've done it in the past. It's in a music venue in White Plains. And the band this year is called Dead Meat. It's a Grateful Dead cover band. You might want to check this out. It's a good event. There was some news today that the council is trying to get together a common bus that would leave somewhere from the vicinity of Melville here on the island to help with our Long Island participants who would like to go. And then of course, in November, the Geology Days conference is being planned right now. You can see there on the slide, November 13th to the 15th. There was a good attendance of about 230 people or so in October. It was an excellent event. You know, a lot of people walked away with 10, 12 hours of PDH credit, but got to see some really good presentations and see old faces that, you know, we hadn't seen each other in a long time. Good things. So check that out. You know, there's more going on in being a geologist than there ever has been. There's an event in the city coming up in the end of the month, February 28th, and it's a Brownfield Partnership conference being put on by women environmental business owners. And you can see there, the website at the bottom there is New York City brownfieldspartnership.org. And you can find out more about that. There's a number of speakers, and there's some really good stories to be told there. So check it out. Let's see, one more here. We've got the Island Rock Hounds is having a gem, mineral, and jewelry and fossil show in Bethpage on Saturday and Sunday, March 18th and 19th. You can see their website there at the bottom if you want to check that out. Good event every year. And somebody's not muted. Could you mute them, Jen? And then there's a list of our sister organizations around the area, the New York State Council, Buffalo, Central New York, Hudson Mohawk, the Northeast chapter of the AIPG, Pennsylvania Council of Professional Geologists, and want to give mention also to Stony Brook University has a geology open night lecture series that they put on. You can go to their website, you can just Google that and you'll find it. But all these organizations have lots of webinars and face-to-face events going on. Never been more content to check out. So that's what that is. So enough about that, and let's get to the main event here, which you all really came for. The presentation tonight is by Dr. Gil Hansen, and it's Hummocky terrain in Suffolk County on Long Island. If you signed up for PDH credit, what we're going to do is there's a couple things we have to comply with for the state education department. Okay, so you have to be here and participate from now till the end of the presentation. We have Zoom actually logs when you log on and when you log off. But in addition to that, we need to verify your attention. So I had put in the chat earlier a code. It's LIPG-214. If all of you could each just type that in now, because the chats get recorded also, and it's a way we verify your presence and participation. If you could do that, and we'll ask for that at the end. There's also 3 quiz questions we'll do. But with that, please welcome Dr. Hansen, and I'm going to stop talking, turn off my video, and turn it over to Dr. Hansen. He's going to rock us. Okay, now, Gil, where are you?
I'm here. You want to stop sharing, I think.
I think I stopped. Oh, there I go. Okay, now, let's get you in here.
Thank you for inviting me for this talk. Behind me is stagnant or dead ice in front of a glacier. I thought that would be a good background. Most people haven't thought about it or seen anything like it. I haven't. And on the topic here, I got into this because when COVID came, I had students do research each summer, going out in the field, collecting samples, doing analysis, grain size, infiltration rate, and a whole bunch of other stuff. But as soon as COVID came in 2020, we were forced to stop. We couldn't do anything inside. So I had to think what we should do that would be still a useful research project. And so what I decided is, let's take a closer look at the topography maps, DEMs, and see what's on there that we haven't really thought much about. And one of the things I talked about already was tunnel valleys. That was really quite exciting to look at the tunnel valleys. But another thing that came up was there's an awful lot of hummocky terrain on Long Island, which we had just ignored. So I'm going to be talking today about the hummocky terrain that we can see in Suffolk County. There might be a similar amount in NASA, but there's so much development, and the development is far enough in the past that it's probably all covered up. So I'm going to share the screen now and get started. Okay, it's the same picture you saw before, and most people know the basic geology, but anyway, this is the Ronkonkoma moraine, and this is the Harbor Hill moraine. Disappeared. The Harbor Hill moraine fell apart. Okay, this is the Harbor Hill moraine, this is the Ronkonkoma moraine. And we're going to be looking at this area here and just see what kind of hummocky terrain we find. Oh, there it is. So what is glacial hummocky terrain? It's a terrain with kettle holes, ridges, and knobs. And they're all sort of helter-skelter. And here is a picture of hummocky terrain in Sweden. Probably not very long after the glacier left this area. So you can see it's quite a mixed up mess. A lot of cobbles, boulders, and stuff at the surface associated with till, and then lots of kettles, ridges, and this one doesn't show so many knobs, but it has knobs in it. Well, so that's typical. This would be a typical sort of look at a hummocky terrain. And so let's take a look then at the Harbor Hill and Ronkonkoma moraines, which consist of push moraine and hummocky terrain. That is that the Ronkonkoma moraine and the Harbor Hill moraine are made up of both hummocky terrain and push moraines. And so let's just take a look right here. And you can see this is push moraine. It's been pushed up by the glaciers. On Long Island, almost all the large moraine features are pushed up. But now you can see this is hummocky terrain. It doesn't have the relief that we have elsewhere. Here you can see a lot of hummocky terrain. Here's push moraines. Here's more hummocky terrain. And on the North Shore, on the Harbor Hill, we have a little hints of it, but not very much. And there might be more here, but the moraine has been eroded off. And we have some right in here, and we have some right in here. So we're going to take a look at the different kinds of hummocky terrain and that we have. But I just want you to know that the Ronkonkoma moraine is not just made up of high hills. It's made up of hummocky terrain and push moraines. So before we go too much further, I think we have to consider the thermal conditions when the ice reached the site of Long Island, because that plays a huge role. The mean annual temperature was minus 10 degrees C or 14 degrees Fahrenheit. And it's been that long enough temperature so that the sediments were in permafrost. So the area was in permafrost. That's important. That means then that any ice that gets buried stays ice until the permafrost melts, thaws. Permafrost doesn't melt, it thaws. In which case the surface thawed, but during the period of permafrost, the surface will thaw during the summer to a depth of about 3 feet. And that's it. So buried blocks of ice covered by more than 3 feet of sediment would probably not melt until the permafrost thawed. So the ice sheet covered the area from about 26,000 to 21,500 years ago. We don't know the exact numbers, but that seems to be a pretty good guess now. Vesna Kundich was studying loess on Long Island that was deposited about 3,000 years ago. She and I visited a number of large kettle holes looking for loess sequences to analyze. We had just a couple of small deposits of loess on campus. And so she wanted to find a really large kettle hole, which would have a really thick sequence of loess. But none of the large kettle holes that we looked at had loess in the bottoms, suggesting that when the loess was deposited, the kettle holes were filled with ice until at least 13,000 years ago. So the whole area was in permafrost, and any ice that was there was probably in the kettle holes were still ice for a long time. And that's a pretty important part here. And so now this is the site of Clara's Woods on the Stony Brook campus. Here's 25A. Here's the main part of campus. This is old, but and this is the Nichols Road through here. The hospital is here, and this is a site of Clara's Woods on Stony Brook University campus, which has a very nice hummocky terrain. And here you can see it. You can see we have ridges, we have kettles, lots of kettles. On campus, we have tens of kettles, ridges, knobs. It's a typical sort of hummocky terrain, knobs. And then we get these sometimes these U-shaped features. This I thought I should mention it. We got ridges are knobs, note ridges and knobs and kettles, but such topography is known as hummocky terrain, but it's also known as knob and kettle terrain, ablation, moraine, ground moraine. So it's got a number of different names depending on where you are. But this is a typical hummocky terrain that we'll be looking at. So how does hummocky terrain form? Well, as the ice approaches, advances to the front of the glacier, it gets thin. The ice gets thin. As it gets thin, the ice slows down. It actually slows down quite a bit, and all of it picks up till, because if it slows down, this is still moving fast, and so now the ice has to start moving up like this, and it pours the underlying sediments up on top of the glacier. And then when that happens, you can get the sediments coming off in flow till. You can get outflow, and here you can see a small proglacial lake, and here you can get buried stagnant ice. So this is an important part. As the ice moves forward near the front, it starts picking up the underlying sediments and pushing them up onto the top of the glacier, which is eroding. Okay, and here is a case where it's including now a push moraine with dead glacier ice. And so here's the glacier. It's approaching the front, so you can see it's pushing up. You get these ice thrusts. You get these beautiful faults and these folds in the ice, and it's picking up the material. And then here's the margin of the glacier, and so this is all dead ice. This is a simple one, so it shows how combining push moraines with melt out basal debris and flowage. So you're going to have all of the sediment that's being brought to the surface is going to be deposited, dumped out. Okay, so let's look at the push moraine part of the Harbor Hill Moraine on Stony Brook University campus. Okay, and again, this is the location of Ashley Ship Preserve. We spent a lot of time in Ashley Ship Park Preserve because when we saw this wall here, we were wondering how could we get a wall like that? And I made the hypothesis that it was pushed up by the glacier because if you have one wall, you have to figure out how it's not a valley wall. If there's a valley wall, you'd have another wall over here. So I had made a prediction that this was going to be a push moraine setting, and a long time ago. And then and so then we got GPR and went in there and tested it. And here is the moraine. You can see here is the ridges, and here are ridges. But if you get further south than about this, it breaks up. So this is more like hummocky terrain down here, but this looks like ridges. So Dan Davis had one of his students do a research project where he went across this with GPR. And then, so he went from north to south, and you can see now, you got the features here that you can see that the GPR is showing that you're having stratigraphy that's being folded, and faulted. And this is what it looks like if you put lines on there. And you can see this is all being folded. Here's a thrust sheet. And so this is very much like a sheet, fold-in thrust field, just like you'd see in plate tectonics for sheets. And then you also see that one of these stratigraphy here is cut off. So it suggests then that the glacier went over the top and cut that off, just cut it right off. It didn't disturb much below it. So this then shows us that we have a thrust, fold-in thrust field, and there is plate tectonics going on. And on Long Island, if you quite often will have a combination in a fold-in thrust or thrust sheets, thrust belts, or thrust moraines, and stagnant ice. And so this is again where we have the GPR. And then when you looked at this, it didn't make any sense. It was not at all a thrust sheet. So this became part of the stagnant ice, dead ice, hummocky terrain. And so then just again repeats what we just seen. You can see here you throw the glacier coming up. This is the dead ice. And then this goes up through here. One of the things that was bothering us is that how can we have holes here? Because if the glacier is going to come over this, it would crush all these things. Well, it makes sense if you have ice in here. And that's what we suppose, is that there is ice that was deposited, pushed up with the other sediments. Okay, and so this is another look at how you can get stagnant zones, and that is you get these thrust sheets up from the ice, and then stuff collected on the front, and then when the ice melts, you get these hummocky sort of terrain, just for the stuff sitting on the top. And then here's another one that happens, is that the ice quite often will have quite a bit of sediment on top. And then if there's a low spot, it's going to start collecting the sediments that are going to be flowing off of here. And they'll be collecting in a pond, for example, or a small pond. And then this could actually have more mud in it than the surrounding stuff. And so then when that ice melts, then you get, actually these turn out to be low areas. These are low areas, and this is high areas. So this be a mound. And so now here is the Hummocky moraine in front of the Astra Brogerbin in Svalbard. And you can actually see this. You get all sorts of mounds and in the area. And you don't see as many ridges in this one like you do in Sweden or on our campus. But these could very well be just small mounds. And of course, there are kettles in here as well. Now, the other way you can get the ridges is that, for example, if you have a pond or something, and you have the ice pushing down on it, and there's just happens to be a crevice there, pushing down on the ice and and there's a crevice, you can actually push the sediments up and form a ridge. And so again, this is potentially how this might have formed. So how to make a kettle. I'm putting this in because even though most people know how to make a kettle, it's important to repeat it, because I found that even if people have known how to make a kettle, they keep forgetting. And so in this case, here's it. Oh, I'm out of shape. Okay, here. Here is a piece of ice, and then if it's above the surface, and it's melt. But you have to realize the ice has to be surrounded by sediments. It can't be sitting. A lot of people think that you have this big chunk of ice, sits on the surface, it then pushes down the sediments, and then when the ice melts, you get the kettle. And the ice when it melts, forms a lake. No, that's not the case. So in here you can see, if you have a chunk of ice, it has to be buried in order to get a kettle. And then here is a case where you get steep walls, and then here you have a shallower kettle. And in this case, you have a deeply buried kettle, and then you get a much slower gradient. In this case, you may not even see much of a gradient at all in here. And then this is how you get water in how you get a pond in a kettle. The groundwater. groundwater has to intersect the bottom of the kettle. And and in the summer or in the spring, you may have vernal ponds where just because of the ground is still frozen, and there's runoff, water's coming down, and then you may get a little pond. In fact, frogs and stuff like those vernal ponds. But if you want to have a pond that stays there all the time in a kettle, you have to have the groundwater above the level of the bottom of the pond. In which case, you can see you usually have steep walls, and then water. Okay, so let's look at the GPR and resistivity of a ridge in Clara's Woods. It'll give us some hint of what's looking on. And this is all of these research has been done by students, not doing a master's thesis, but probably a small research project. So we haven't had anybody, which would be nice if we could have had go through and do a research. So we just chose this ridge because it's a beautiful ridge, and went across it and looked at the GPR and resistivity. And so we're going from east to west on this, here to here. And these red dots are probably boulders or cobbles. You can see some stratigraphy, and you can see it's folded a bit in here, or folded, at least it's been changed orientation. But right in the middle here, you get a featureless area. And ground penetrating radar doesn't like to go through mud. The mud it's got water in it, and that slows down, that modifies the signal of the GPR. So you don't get a good return signal on it. So this is really a featureless area. Is probably mud. Then if we go to resistivity, the dark colors here are high resistivity, and this area is very low resistivity. And so that matches pretty well with this area here. And it's suggesting then that there was mud there, and this could have been a small pond where mud had been collecting, and then the ridge was being forced up, perhaps by a crevice in the overlying ice, and we get this feature then. And here we get some more muddish type things there. And this is probably mostly till, which has high resistivity. And so this would be the model then, that this is the ridge. It's being pushed up, and there's probably some mud in here. It's being pushed up along with the other sediments. And again, this would be then a crevice. This scene is very similar to what we have on campus for the Hummocky terrain, with the kettles and the ridges. And so now let's just take a look at what it might have looked like at the time of the formation of the Hummocky terrain and the thrust sheet material here, and the outwash. So this is about where the level of what the active ice was. South of that, this is north up here. South of that, we pretty much see Hummocky terrain everywhere, here and here and here. And then, so this is the stagnant ice. And then what's interesting is the outwash. some of the outwash itself is actually lapping up onto the onto the hummocky terrain. And you can see the break is quite strong in here. You walk along it in the stagnant ice area, you're going to get these features here. But at the same time, you're going to also see a lot of boulders, cobbles, and stuff. But it really appears that it's lapping up onto the stagnant ice. No, up to the stagnant ice. It's not clear then what the relationship is of the hummocky terrain to the outwash. We'll talk about that more later. So let's look at the Ronkonkoma moraine. Now, in this case, now we do have studies on the two push moraines. This is a Selden moraine, and you can see it's way behind the main part of the Ronkonkoma moraine. And so, for whatever reason, the ice decided to make a push moraine here. And then this is then Bald Hill in here, and this is again forming about probably at the same time, but it's a different one. And this one was Chantavelia did the study on this, and then I forgot her name right now, but did a study on here, a student. So let's take a look. Oh, and then here we can see right next to the moraine, you get hummocky terrain. So the glacier ice came to here, and you actually can see the outwash is lapping up onto the hummocky terrain right here. And that's probably the boundary of the ice right there. So it's probably, that's the boundary of it there. And the boundary of the ice is going to be something like here. And so then there's a close-up of the hummocky terrain. So you see it looks quite similar to what we have on campus. So now these are the two ridges that this is the Selden Ridge, and these are the ridges that Chantavelia worked out. And these are the ridges that Kristen Rosa was working on. She just did a part of it because this is a much larger area. So she only took a small part of the thing just to see, is it really a push moraine? And so here is Chantavelia's situation. And so he's going to look at it through ground penetrating radar. And this is a line across it. I don't know why he took such a funny picture, but you can see here is going from the north to the south. The glacier traveled through here, and you can see it clearly is a push moraine with all of these fold and thrust sheets. Okay, so that is there's no question that's a thrust. And this is then Rosa has done this. She just took one ridge here and looked at it. And oh, yeah, okay, so she went from north to south, and these are the ridge. And then here is the glacier is pushing in this way. And again, you can see she's getting fold and thrust sheets in here. And so again, there's no question this is a fold and thrust sheet. So it's a push moraine. So we get the two things we got combined. And the moraines here tend to be push moraines, and the hummocky terrain is just where the glacier sat still and didn't happen to push the material up. So let's take a look at the hummocky terrain along the Ronkonkoma moraine. So in this case, we'll just go across here. And again, you can see you got the hummocky terrain here. I'm not going to deal with this. I think it's a interlobate moraine that's been cut. But you can see here, this is probably pushed up here a little bit, but this is all hummocky terrain. This is all hummocky terrain, and all hummocky terrain here. All along, beautiful hummocky terrain. So the Ronkonkoma moraine in this case is dominantly hummocky terrain until we reach. So that's a large stretch of it. Okay, so then this is looking further to the east at some evidence for hummocky terrain. And so this is going to be Bridgehampton here, and East Hampton is here. And let's take a look at these areas. So now a number of people have talked about the Scuttle Hole ponds. Fuller did, Soma Sen did, and they're really interesting. They look like there could be, they look like they're potentially kettles. We'll come to them more again. And then this area is going to be, see this? This area is hummocky terrain. And it looks like it's a small plume of the ice went further to the south here, and here's another one. So the Scuttle Hole ponds are ice-filled kettle holes. This is the hypothesis. Were covered with sediments which stream crossed after the Ronkonkoma moraine. So let's take a look at it. Here are the Scuttle Hole ponds. And you can see the streams go right across. There's no way they would do that. If these were holes, the water, the stream would not know to go across it. It would probably go into the pond, and then we have overflow and overflow here. But it would not, in any case, go across like this. Oh yeah, I think it was Brett Bennington also mentioned this in his talk. So these had to be frozen, and they had to have at least 3 feet of sediment cover on them, so that they wouldn't have, the ice wouldn't have melted, and so these little streams that are coming across don't even know that there's ice underneath. And here's a picture by Soma Das. Her name was Soma Sen. Then she got married during the time I was dealing with her. So she's also known as Soma Das. And so you have frozen outwash. And here is the buried ice. And then she uses sort of a brownish color just to locate where the ice is. And then it's covered by sediment. And you can see then that the streams are just coming across it, don't know that the ice is down below here. Okay. And so hummocky terrain show, so the odds are then that if this is a part of a hummocky terrain, which may or may not be, that would suggest then that the outwash after the hummocky terrain here formed, the outwash, enough outwash covered the area such that the outwash features got buried. Why we have them in a row, I don't know. That's a separate issue. The Scuttle Hole depressions, why are they in a row? Okay, hummocky terrain show that small lobes of Ronkonkoma moraine extend to the south of the moraine. Okay. And so these are the two. These are a closer look at them. And you can see clearly looks like hummocky terrain. But I was very bothered by the fact that if you look at the global mapper now, you're seeing the area is completely developed. And so I don't know how much of this could be related to development and how much of it's related to original hummocky terrain. So we just take this one. This is this one here, and take a look at it. This is the one that's in East Hampton area, and so take a look there. And so I got a 56 or 57, 1 to 24,000 topo map, and you can see that the black dots are, of course, where there's development. There's not much development at this time. And of course, the map was made probably well before 56 or 57. And you can see all of the topography here. You got kettles, you got funny ridges, and quite consistent then with this being a hummocky terrain. Not as well exposed as the had, because this I think has a 10-foot contour interval, whereas this one you have you're using a laser DEM, so it's probably on the order of only inches relief on certain that you're able to measure. And so then I think this is really shows then that this one is the hummocky terrain is showing you that there was a small plume that came out south of the glacier, and this is the one to the this is now going to look at the one further to the east, and here we can see again this looks like good hummocky terrain. And then again on the 56 or 57 topo, there's more development here, but again, you can see all of the, look at the holes, kettle holes, ridges. So it's quite consistent then, and since there's not been much development up till that time, that this again shows another small plume of the glacier moving to the south. Okay, so let's take a look at another place. We're going to look up right in, we're particularly interested in this area right here and through here. And now why is the hummocky terrain here? This is the Ronkonkoma moraine. This is the push moraine type topography. And you can see immediately south of the moraine, that's hummocky terrain. Really nice hummocky terrain. And so it suggests then that as the glacier, Ronkonkoma moraine, Ronkonkoma ice sheet retreated to the north, it was retreating fairly quickly and leaving ice, dead ice, which is leaving instead this hummocky terrain here. And you can actually see hints of it over in here, lots of hints of it. And this, of course, is outwash and through here. So that would suggest then that the hummocky terrain is forming here. And then the big question is, how far to the north did the hummocky terrain go? And And then this is, of course, outwash covered, but there are hints that there are places in here where there are little places you can see the outwash that's sticking out above the through the outwash, probably because there were chunks of ice high enough that the outwash couldn't cover it. And the outwash is not very thick. And then, oh, did I just do that one? Yeah, this is again a little bit further. This is Northville. And again, we get hints of Hummocky terrain along this area and through here. Little hints all over. And so it again says that underneath the outwash, there was hummocky terrain. Oh, I gotta go the right direction. Okay, and here we get to see fairly large areas of hummocky terrain. If you've been to Rocky Point, walk through this area, this is really large kettles. I went with my grandson in 2019 because we wanted to see the character of it. And when you're walking around it, it's really quite large, and you have to keep your eyes really peeled because it's covered with vegetation. But you can see these are really good hummocky type terrains. And then here you got again hummocky type terrains. Let me see. I want to get you a better chance to see it. Again, that sure looks like hummocky terrain. And then this is a deep pond. It's in an area where we're probably in a hummocky terrain type area, so it's quite reasonable that you get a big kettle hole. And then Lake Panamoka is in here in a hummocky terrain. And then this is what I'm hypothesizing, is that you had a fairly large chunk of ice that was covering the area. And then so that the outwash that was coming off the front of the glacier is not able to deposit anything in here. And so that's why you have a good hummocky terrain. And the same thing here. That would be an area that was covered by a big ice sheet, a block of ice, or maybe multiple blocks of ice. And that prevented then the area to be covered with outwash. Okay. So I've dumped a lot of stuff on you. I hope it's somewhat understandable. So as the Ronkonkoma ice sheet retreated, it left a hummocky terrain. And this is something that bothers me. Or could the hummocky terrain be from the retreating Harbor Hill ice sheet that advanced and retreated the Harbor Hill moraine, where it remained for a while? We don't have a continuous exposure of the hummocky terrain. But I'm sort of suspicious that the retreating Ronkonkoma ice sheet left hummocky terrain all across Long Island as it retreated to the north. And then the Harbor Hill moraine just sort of developed on top of it. So in any case, the outwash from the Harbor Hill ice sheet is thin and in places does not cover all of the hummocky terrain. Where large areas of the hummocky terrain are exposed, large blocks of retreating ice may have been left that was much thicker than the outwash which was deposited around the ice. That would be the main conclusion. Summary. The Harbor Hill and Ronkonkoma moraines in Suffolk County are mixtures of push moraines and hummocky terrains. And so they are moraines. You can have it as a moraine made up of hummocky terrain, but you have to realize they're just not all high areas. It's a combination of high areas produced by push moraines and lower areas made up of hummocky terrain. Hummocky terrain in small patches south of the Ronkonkoma moraine suggests that small lobes of the Ronkonkoma glacier advance south of the moraine. The north side of the Ronkonkoma moraine consists of hummocky terrain with little to no Harbor Hill outwash covering the terrain. Further to the north, patches of hummocky terrain are surrounded by Harbor Hill outwash. This suggests that as the front of the Ronkonkoma glacier retreated north, it left stagnant ice behind, which produced the hummocky terrain between the Ronkonkoma and Harbor Hill moraines. Thank you. The end.
Thank you, Gil. We actually have a question already in the chat. If anybody else has any questions, please feel free to put them in the chat, or you can unmute yourself and ask them. The first question is from Rich Baldwin. With global warming and glacial retreat, are we seeing current examples of this phenomena?
I really can't answer that. I'm sure that would be the case, because as a glacier retreats, it's going to be leaving behind a hummocky terrain, because it can no longer keep pushing. In order to have hummocky terrain, the glacier is not advancing over the hummocky terrain. So if it is retreating, you'd expect there to be hummocky terrain and more hummocky terrain left. And this suggests, what we're seeing here suggests that the Ronkonkoma moraine retreated quite fast off of Long Island before the Harbor Hill moraines formed. I don't think it was due to warming. It's because the ice was changing the rate of front of it rate advancing and retreating.
Okay, we have another question from Brett Bennington. Do you want to unmute yourself to ask the question, Brett?
Yes. Thanks, Gil. That was fascinating as always, and gives me a lot to think about. My question concerns the small erratics and the till that some people who've worked with you in the past have reported south of the Ronkonkoma moraine. Do you think that material represents a significant advance of the ice further south of the Ronkonkoma moraine? Or do you think maybe that those are just patches of material deposited by a few lobes of ice that, you know, made it a little bit farther south?
That's a good question. I didn't bring this up here, but when they did dating of exposure ages of boulders in Martha's Vineyard, Cape Cod, and then further north into Connecticut and Massachusetts, they found that they had, just as you get to Connecticut, that gives about 18,000 year exposure ages, 19,000 years about in Cape Cod area. Martha's Vineyard gives 23,000 year old exposure ages. It could very well be that we had the glacier extended further south into the ocean, which is now the ocean, was the ocean then. And those boulders could have been formed at that time. If there was a 24, if we had it, exposure age is not dating the time of deposition, it's dating the time that the boulders were exposed to the cosmic rays. So whatever makes the age younger or older. It's probably just mostly snow and stuff like that. So it could be we could have had plumes or of ice coming from the north, but I can't see that on the DEMs. I see the ones to the east. They stand up very well. But that's an interesting problem. Why do we get the big boulders down there on the south shore, on the south side of the Ronkonkoma?
They're not associated with hummocky terrain that you can
Well,
tell?
they could be, but then the hummocky terrain would be covered by outwash.
Oh, I see, right.
Yeah, they would be covered by outwash. Because you get the if there was a 23,000 year, it would probably be more like 25,000 retreated across the area. Then the Ronkonkoma moraine came, then it would be dumping a lot of outwash and could have covered any of the hummocky terrain.
Right. Thank you.
Thanks, Brett, for that question. I don't see any other questions in the chat, but please feel free to add something or to unmute yourself if you have a question.
I have another question, Gil, while I have you on the hook here. Has anybody gotten any exposure ages for boulders in the Ronkonkoma moraine?
Yes. They never got published for whatever reason. They have the same age as the Harbor Hill moraine, 18,000. And the Harbor Hill moraine comes out 18,000 as well. And but there's about 1,000-year uncertainty in both. So that would suggest, though, that based on exposure ages, that there's not a heck of a lot of difference in age of the Ronkonkoma moraine and the Harbor Hill moraine. And that would go along with the fact that the Ronkonkoma moraine just got the heck out of there really fast, or the Ronkonkoma moraine, but the Ronkonkoma ice sheet.
All right, that's news to me. That's interesting to know.
Yeah.
Because I had always kind of assumed that the Ronkonkoma moraine was, a bit older than the Harbor Hill moraine, but
Yeah, it is probably. It could be 2,000 or 3,000 years old.
right.
All right, doesn't sound like there are any more questions. Chris, do you want to do the PDH questions?
Indeed, I do. Thanks, folks. And Gil, another fascinating presentation. Excellent. Thank you so much. One thing I'm sharing, I should be sharing my screen. Why is it not doing it? One thing I neglected to mention was with the New York State Council of Professional Geologists annual meeting on March 16th. There will be a presentation made by Eric Greppo, who's the Executive Secretary of the Engineering, Land Survey, and Geology Board. That's the interface with the State Education Department. There'll be a presentation about licensure, where it's going, where we are, and opportunities to ask questions and get them answered. So, that's something you might want to consider participating in. But with that, let's get to the questions here. I'd given you the code earlier, LIPG-214. It would be appreciated if everybody could check in the chat box and then try and answer these questions. There's just 3 of them, but that's how we record that you're still here and eligible for the PDH credit. So with that, the first question: what is the geology term for a small knoll or mound above ground? A, a dune, B, a mountain, C, a hummock, or D, a hill? Give you a minute to punch those in. The answer should be pretty obvious following Dr. Hans's talk. All right, I'm gonna keep going here. A blank is a depression / hole in an outwash plain formed by retreating glaciers or draining floodwaters. Kettle Lake, kettle hole, pothole, or D, all the above. Hopefully, if you were paying attention, this stuff's easy. What is that? Gene, you're playing with your pencil there. And the last question, the hummocky terrain is only found on Long Island. True or false? All right, those are our questions for the evening. Last call for questions. All right. Well, we had 80 folks turn out. That might be a record for these webinars. And as I've mentioned before, we started doing these during COVID in 2020, and most all of them are recorded. And if you're interested, you can go to the LAPG website under the multimedia tab. There's quite a few webinars recorded there, and on a number of topics. The content is a lot of variety there, and you might want to check them out if you're looking to get into some more of this stuff. Lastly, I'll just say again, the appeal for folks to come on out and participate by helping put these on. We'd very much appreciate it. Getting speakers is a full-time job to keep this up on a monthly or at least quarterly basis. So that's it. If there's nothing else, I'm going to say thank you very much and have a great night and a great weekend.
Thanks, Chris. Thanks, Gail. Have a good night.